In this video, what I'm going to discuss is what we call inverses of relations and one-to-one functions. Okay, this is not a difficult concept. Okay, let's say I have a relation here. Remember, a relation is just a set of ordered pairs. Okay, these happen to be a set of ordered pairs of real numbers. In fact, positive integers, as a matter of fact. Okay, so here's our relation here. 1, 2, 2, 3, 3, 5, 4, 7, 5, 11. The domain of R is what? 1, 2, 3, 4, 5. The range is 2, 3, 5, 7, 11. I've written that as an arrow diagram down here. Okay, so this is relaying exactly the same information as that as a set of ordered pairs. Okay, and now I'm going to talk about the inverse relation. Okay, the inverse relation is found by taking each of the ordered pairs in the relation and just reversing them. Nothing more. So we're just reversing the order of the elements making up each ordered pair. Okay? So instead of 1, 2, we're going to have what? 2, 1. Okay? 3, 2 instead of 2, 3. 5, 3. And 7, 4, and the last one here, 11, comma 5. Okay, so that's its inverse relation. Okay, we're going to see how these two relate geometrically. By the way, if I was to graph this in the xy plane, what's the geometrical relationship between those two? Well, we'll discuss that in a later video. Right now, I'm going to go ahead and write R inverse here. By the way, that exponent there, that's not the reciprocal of R or anything like that. I know that's kind of a bad notation, but we're stuck with it because I'm not the math dictator. I would prefer a different notation, but that's written R inverse, okay? Not reciprocal. All right. What's the domain of R inverse? Well, it's the set of all what? First elements here. So that would be what? 2, 3, 5, 7, 11. And the range elements would be what? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 here. Okay? Now, you got to get to the arrows pointing the right direction. Again, you guys in your arrow diagrams, or your maps as some people call it, don't forget to get the little arrow head on there, showing which way the arrow is pointing here. Okay, which one is the what domain element and which one's the range element, in other words. Okay, so don't forget your arrowheads. Considering where we live, it ought to be easy to remember that. Okay, now just a quick comment here. Do you guys notice something that's pretty obvious here that I will write down formally later? That what the domain of R inverse is really what? The range of R, right? Because, well, that makes sense because all they did was what? Interchange the set of elements in all of the ordered pairs. So this is pretty clearly that's going to be the range of R. The domain of R inverse is going to be the range of R. Likewise, the range of R inverse, because of that reversing process, is actually going to be what? The domain of the original R. Okay? All right? Some people draw these by just what? Switching the direction of the arrows. Okay? Switching the direction of the arrows. But I don't like doing that, at least not right now, because what? I said my default position was always to have the domain on the left-hand side and the range elements on the right-hand side. So we're reading from left to right like reading a book in the West, anyway. Here's a quick question for you, just looking at this one. Is R a function? Does this pass the test that corresponding to every element in the domain, there's only one element of the range? Yep, it's not doing this, right? This would not be allowed. You know, if this was pointing at, say, 3 also, that would make it a non-function, just, you know, a relation. Yes, I think it is, actually, isn't it? So we'll go ahead and answer that question. It looks like corresponding, it doesn't look like it, I'm certain of it, corresponding to every element over here, there's only one element over here. How about R inverse? Is that a function also? Well, now I have to remember the direction of the arrows has changed, so I have to look here. Is it true that corresponding to every element of the domain of our inverse, there's only one element of the range here? And that's also yes. Okay? Now, a function that satisfies a condition like this, okay, is sometimes called a one-to-one function. Okay, now I wrote it up here, one-to-one, but sometimes I'm a little lazy. Well, not sometimes, usually. Usually I'm pretty lazy and I write what? Just that. That's one-to-one function, okay? One-to-one function. What is that? That's a function whose inverse is also a function, okay? So a function whose inverse is also a function is called a one-to-one function. And we'll explain a little geometry associated with that in a few minutes here. But take some examples first. R is a one-to-one function, right? Yeah. All right, let's take an example where you aren't getting a one-to-one function. So I'm looking for an example, I'm calling it here H, where it is a function, but it's not one-to-one. And we'll see why here in just a second. Maybe I'll do this one in red because it's bad, okay? Okay, well, is this a function? First of all, the domain is what? -1, 1, 2, 4. The range is 1, 3, 0. Is this a function? Yeah, corresponding to every element over here, there's only one element over here. It isn't doing that thing, right? Reading from left to right, look at the direction of the arrows. But it's actually not one-to-one, because what would happen if I create the inverse relation here, okay? I'm going to just change the direction of arrows. So 1 is pointing at -1, and 1 is also pointing at what? 1. Remember, the direction of the arrows is changing. That's equivalent to what? Just interchanging all the ordered pairs, okay? 3 would be pointing back at 2, and 0 would be pointing at 4, okay? Now, if you look at this, this is a relation. It can be considered ordered pairs here, but is it a function? The answer is no, okay? Because corresponding to the element 1 in the domain of H inverse, there's what? More than one element of the range. In fact, there's two of them, both -1 and 1. So that kills it, right? Whatever else happens with these guys, it's over. It is not a function. So this is not a one-to-one function, right? Why? H is a function, but what? H inverse is not a function. So H is a function, but not a one-to-one function, right? Now let's come back and let's go back and talk about, okay? If you think about it, you've got what? Corresponding to every element of the domain, there's one element of the range, and vice versa. That's where the one-to-oneness comes in, okay? And let's continue here. I'm going to take just a geometrical approach on H here that we've got. I'm going to take these. You see these are ordered pairs here. Okay, these are ordered pairs. I wrote them as ordered pairs then. -1, 1, 1, 1, 2, 3, and 0, 4 here. This I'll use black. Okay, and I just plotted them in the XY plane. Now if you were to look, remember my entire relation just are points in the plane, right? This. How do you know it's a one-to-one function or not? Well, what would be the corresponding test for every y value that corresponds 1 or no x values, right? That's what you'd be interested in, like in this case, because you interchange the x and y values to get the inverse relations. The answer is you would have what we, right? This would mean what? Every horizontal line intersects the graph at most one point. And you can see this actually fails here. Imagine equals 1, it would actually intersect this graph at 2 points. Rather, discuss here is the composition of a one-to-one function with its inverse. Let's go ahead and try this here. Here I'm going to take the same r I had originally. So 1 points at 2, 2 points at 3, and so forth. And I've got its inverse right here. Now let's go ahead and compose these. Remember how we did that in a previous video? Okay, it's basically just following the arrows. Now in the order, I've got it written here, the thing that's being composed first, or the computed quote unquote first, is the R. So remember, this is going to correspond to what? R inverse composed with R, because you've actually got to remember our other notation, R inverse of R of X. If you evaluate that for various values of X, right? You're actually computing the R first. Okay, so let's see. 1 would point at 2, 2 would point at 1. So 1 points to 1, ultimately. 2 points to 3, 3 falls into R inverse and changes back into 2. Do you see what's happening here? 3 goes to 5, but 5 goes to 3. So when you're composing the R of 4 is 7, R inverse of 7 is 4, so you went back. So 4 started with 4 and you ended with 4. 5 goes to 11, but R inverse takes 11 and turns it back into 5. Now look at that function there. What would you say that function is? It's what we would call an identity function. See, what comes in comes out, right? That's what we mean by an identity function, okay? So this is an identity function. The reason why I just say it's an unidentified, an example of identity function, is that its domain is somewhat restricted, right? What's the domain of this composition? The domain is 1, 2, 3, 4, 5, the domain of R, okay? Let's reverse this though. Let's go R composed with R inverse, so I've got to compute R inverse first. 2 goes to 1, and then R takes 1 and turns it into 2. So this goes from 2 to 2. Okay, 3 goes to 2, and then R takes that and turns it back into 3. So we've got 3 goes to 3, 5 goes to 3, goes to 5, 7 goes to 4, back to 7, and 11 turns into 5, but R takes 5 and turns it back into 11. Once again, you see it's an identity function, okay? What goes in comes out, okay? But notice it's not the same function here, okay? These are different, okay? But they're both identity functions in the sense that what comes in is exactly what comes out. But this has what? A domain, you'll notice, that is actually what? The domain of R. The domain on this one is what? The domain of our original function, the first one that you're computing, which is actually what? R inverse. So they have different domains here. And of course the ranges are exactly identical. Okay, this is what I want to say though. The composition of a one-to-one function with its inverse in either order is an example, it's an identity function. And then I've written that here. If R is one-to-one, F composed with F inverse composed with F of X is X for all X in the, do you guys know that notation? For all X, an element of the domain or belongs to the domain of F, okay? And that's the example we saw here, like that. And the second, if I go F of F inverse, okay, F inverse is computed first, but still it just ends up being just X. Whatever dropped in will drop out, so long as what? X is in the domain of F inverse, which is exactly the same as the range of F, okay? So this is what I wrote here. And I threw this in here at the end just for emphasis. If F is one-to-one, the domain of F is the same as the range of F inverse, and the domain of F inverse is the range of F. That just corresponds to what? This idea of switching all the ordered pairs, okay? Switching the order of the elements in each of the ordered pairs. Anyways, okay, well, I hope you understood that.